Hello. Hello student. In today's lecture number 2. Hello student. In today's lecture we will study application of refraction of light. In application of refraction of light, we will see whenever any observer from rarer medium views any object in denser medium, then what happens? And whenever any observer from denser medium views any object in rarer medium, then what happens? What is apparent depth, what is actual depth, and what is lateral shift, okay? And what is critical angle? These things we are going to study here. Total internal reflection, all these things we are going to study here. So critical angle, total internal reflection, and application of refraction of light. These things we will study today. In application of refraction of light, first we will see lateral shift. Dear student, here is some medium slab. Having refractive index mu. Let us assume thickness of the slab is T. And light ray is coming from air, incidenting at point B. AB is incident ray. This is angle of incidence. Since light is moving from rarer medium to denser medium, so it will shift towards normal. This is angle of refraction. And since light ray is again moving from denser medium to rarer medium, it will again be parallel to the incident ray. Had this slab could have not been here, then light ray could have been moving in a straight line. Because of the presence of this slab, the light ray has shifted backward by this distance x. This x is called lateral shift, okay? Let us assume this point is D. Now we have to determine this lateral shift x, okay? Let us assume this point is E. What we are doing to determine lateral shift? We are drawing perpendicular here. This dn is perpendicular to this direction of incident ray, okay? This is normal. This angle is r, this angle is I, so this angle is how much? This angle is I minus r. Now we are looking in triangle BDN, okay? BDN. What we are observing here? Sin I minus r equal to dn, that is x. The side opposite to 9 degrees hypotenuse, that is BD. BD is what? Optical path length, okay? So dear student, what is x here? X is BD sin I minus r. This is equation 1. Now let's see triangle BED. What is quasar? Quasar equal to T upon BD. So substitute this value of BD here. X equal to T sin I minus r upon cosr. When angle of incidence is small, you can apply sine rule here. You can apply Snell's law here. 1 into sin I equal to mu into sin r. In case of small angle, I equal to mu r. So you can calculate value of I and r. In case of small angle of incidence, x equal to t I minus r. Okay. You can substitute all these value and can find lateral shift. Okay. So this x can be written as ti 1 minus r upon I, and then r upon I can be written as 1 upon mu. In this equation, value of I should be written in radian. This is the way in which we will be calculating lateral shift. Okay. Now let's see one very important phenomenon, that is whenever any observer from rarer medium will view any object in denser medium, then you will see the image of the object will come closer to the medium interface, and the distance by which image of the object gets shifted up is called normal shift. Okay. And distance of image from the medium interface is called normal shift. Let's see. Observer position. In denser medium. Observer position in rarer medium. And object position in denser medium. Now see here. This is the diagram. Let us see. This is a denser medium having refractive index mu d. This is a rarer medium having refractive index mu r. Sometimes this remains air. Okay. And this is normal to the refracting surface. Let us see. This is the object. This is point A. This is the actual depth of the object. Whenever any light ray move from denser medium to rarer medium, it will shift away from normal. If this angle is angle of incidence, this angle is angle of refraction, If we retrace this light ray, this is the position of image. Remember, this image is getting formed in a medium of this rarer medium, okay, where refracted rays are moving. Remember, this location, position of this image is existing in rarer medium where refracted rays are going, okay, because object is here in denser medium. In case of refraction of light, always remember, object and image always remains in different medium, okay. In case of refraction of light, object and image always remains in different medium. Here, in case of, here object is in denser medium, so location of this image will exist in rarer medium at a distance AI, okay, at a distance AI from medium interface. Now, dear student, if this is I, this is R, so this is also I, this is also R, okay. And this AI is called apparent depth. And this OI is called normal shift. Now, dear student, let's apply Snell's law, 8.B. 8.B, we are applying Snell's law. Mu D into sin I equal to mu R into sin R. So sin I upon sin R equal to 1 upon mu dr. This is equation 1. Now, let's see triangle AOB. When angle of incidence is visible, we are assuming sin I equal to tan I. Equal to what? AB upon H actual. In triangle AIB, we can see sin R approximately tan R equal to AB upon H apparent. Now we are dividing equation 2 with equation 3, we get sin I upon sin R equal to H apparent upon H actual, okay. Divide equation 2 and equation 3. We get sin I upon sin R equal to H apparent upon H actual. And sin I upon sin R equal to 1 upon mu dr. So dear student, now final equation is H apparent equal to H actual upon mu dr. Since refractive index of denser medium with respect to rarer medium is greater than 1, therefore H apparent is less than H actual, okay. So image of the object comes closer to the medium interface. And what is normal shift? Normal shift is OI, that is what? AO minus AI, that is what? H actual 1 minus 1 upon mu dr. This is the normal shift. The same is the case for velocity also, okay. Apparent velocity will be equal to actual velocity divided by mu dr. Same is the case for the acceleration also. Now, dear student, let's see the next case when observer will be in denser medium and object will be in rarer medium. Object position in rarer medium. And observer position in denser medium. So you will see here, whenever any observer from denser medium view any object in rarer medium, then the position image of the object will appear at more distance than the medium interface. Okay. Let's say this is the object position. This is H actual. This is rarer medium having refractive index mu r. This is denser medium having refractive index mu d. When light enters from rarer medium to denser medium, it will shift towards normal. Dear student, in this case, this is object and this is image, okay? This is the apparent height. This is angle of incidence and this is angle of refraction. This opposite angle, this is R, this is R. If this is I, this is also I. If this is R, this is also R. Now applying Snell's law at point B. Apply Snell's law at point B. We get mu d into sin R equal to mu R into sin I. All angles will be measured with respect to normal. So here sin I upon sin R equal to mu d upon mu R. This is equal to mu dr. This is equation 1. Now, in triangle AOB, sin I equal to AB upon H actual. In triangle AIB, sin R equal to AB upon H apparent. Divide equation 2 with equation 3, we get sin I upon sin R equal to H apparent upon H actual. Okay, so now you will see. Divide equation 2 and equation 3. We get sin I upon sin R equal to H apparent upon H actual equal to mu dr. So finally we get H apparent equal to H actual into mu dr. Since a refractive index of denser medium with respect to rarer medium is greater than 1, so apparent height is more than actual height. So dear student, whenever any observer from denser medium will view any object in rarer medium, then the image of the object will appear at more height than its actual height. Okay, this is the case. Now let's see about the critical angle and total internal reflection. Let's see about the critical angle and total internal reflection. Critical angle and total internal reflection of light. Dear student, how do we define critical angle? Whenever any light ray move from denser medium to rarer medium, it angle this critical angle, then angle of refraction becomes 90 degree. This angle is called critical angle. And what is this critical angle? Mu d into sin theta c equal to mu r into sin 90. So sin theta c equal to 1 upon mu dr. This is how we define the critical angle, okay? For red color light, lambda is maximum. If lambda is maximum, mu is minimum, sin theta c is maximum, and theta c is maximum. So red color signal are used as a dangerous signal, okay? Because critical angle will be maximum for red color signal, okay? Now, dear student, what is TIR? Total internal reflection. Total internal reflection of light. When any light ray move from denser medium to rarer medium at an angle more than critical angle, then light returns back to same medium, okay? This phenomenon is called TIR, total internal reflection, okay? This event is actually the event of refraction. But since light ray returns back in its original medium, so laws of reflection gets valid, okay? This angle will also be again I. So how much is the deviation? This is I. So deviation in this case is how much? 180 degree minus 2i. And what is deviation in this case? Deviation in this case is 90 degree minus theta c, okay? If I becomes equal to 90 degree, this deviation becomes 0, okay? So this is how TIR is defined. If we draw a complete graph for a light ray moving from denser medium to rarer medium, complete graph for a light ray moving from denser medium to rarer medium, this is angle of deviation and angle of incidence, okay? Light ray moving from denser medium to rarer medium. This angle is called critical angle, and this is pi by 2 minus theta c. Then after sudden jerk is there, reflection start, okay? And this deviation becomes pi minus 2i, okay? And when this I becomes equal to 90 degree, deviation becomes 0, okay? Here discontinuity in the graph takes place, okay? This is the graph for a light ray moving from denser medium to rarer medium, okay? Now, dear student, in the next lecture, we will see application of TIR, okay? Thank you.